My presentation will be about urban scale measurements, meaning, first of all, meteorological measurements of weather and climate properties. And I will start the lecture with general introduction of challenges which investigate or model or predict or measure the urban climate. Here we have some very specific challenges. First of all, it's spatial heterogeneity. Urban areas are represented by different land covers, different morphologies, different architecture, and all these properties, of course, affect a local microclimate and determine very high spatial heterogeneity of urban environment. And each piece of this heterogeneity interact with atmosphere with different scales. For example, we could have microclimate of specific courtyard, local scale climate zones with more or less homogeneous environment, and urban boundary layer developed by the city as well. So different scales, different processes, so quite complex situation. And very important issue, especially for Russia and developing countries, is lack of observational data. So this is what it is about our lecture. Typically, regular weather stations where routine weather and climate monitoring is carried out. These stations are typically located outside urban environment and characterize surrounding rural landscape. So this is typical situation for Russian city when weather station associated with this city is located outside the city. So from this station, we will know nothing about urban climate of this city. We will get information only about rural information. And scientific direction during last decades, many types of measurements are proposed to get information on various special scales and for various tasks. And we will cover, of course, not all of these measurements, but some which we found more relevant. So there are, of course, the basic regular measurements at weather stations, which could be as well regular stations of national networks or specific urban networks. Another very popular type of measurements is measurements from moving cars. Also, there are specific masts, which allows to measure not near the surface, but above the surface layer, so in the lower atmosphere. There are remote sensing equipment as well as ground would fly and measure information above the surface, aircrafts, drones. So more details will follow. And I will start my part with a brief introduction of urban flux measurements, because expensive and probably most expensive type of measurements that could be ever conducted. But these measurements are needed to understand the energy balance. So to understand how the surface interacts with atmosphere. And because this interaction is the primary mechanism which determine microclimate and climate in general on the larger scale. And when we are speaking about urban and atmosphere interaction, we need to know the energy exchange in terms of fluxes. Some fluxes, energy fluxes, are determined by radiation, so it's upcoming solar radiation, infrared radiation, and very important fluxes are turbulent fluxes of heat and humidity. So in other words, sensible and latent heat fluxes. They are determined by atmospheric turbulence, by small eddies which exist in any type of environment. They are mixing, and they are determining energy exchange between surface and atmosphere. And the only one reliable method to directly measure these very, very small eddies is eddy covariance method. When we measure regular parameters such as wind speed, temperature, humidity, but with very high frequency, about 20, typical frequencies 20 hertz or 20 measurements per second. And this allows us to calculate covariance. So covariance are very small scale anomaly from the mean state, and then determine the fluxes. So what we need to measure the balance. And such measurements are carried out by very expensive and high quality equipment, acoustic anemometers, and very high frequency gas analyzers. And when we making measurements in urban environment, it's also very important to have such measurements inside the urban canopy and above, to get information about how the whole landscape interact with the atmosphere. And for this task, research groups are developing meteorological masts, which extends for several tens of meters. And this is, of course, not so easy to develop such mast in urban area. So there are a few of such measurements in all over the world, and probably the most known is a bubble experiment in Basel, which is an example for all follow-up groups how to do such research. So you can see this mast. It's installed in the urban canyon, and there are measurements near the surface and at several vertical levels. And on each level, there is eddy covariance equipment which measures these small scale fluctuations of the wind speed, temperature, humidity, in some levels also CO2. And this are between the urban surface and the atmosphere. And this is some examples, some other examples. So this is how eddy covariance equipment looks in a field study of cross calibration. This is not urban area, but such cross calibration is very important. And this is our new map, which exists in Moscow State University, new mast in Moscow State University, which is operated since 2019. It's another example. It's not a mast. It's eddy covariance measurements inside the street canyon in Moscow a few years ago. It was during in the beginning of my PhD. And this experiment was done together with Pavel and colleagues from Aymobukhov Institute of Atmospheric Physics. And this is probably the most advanced example of most advanced urban flux measurements in the world from Helsinki, Smer 3 station in Kumpala campus. So it is a very advanced mast with different levels and many, many parameters measured. So there are a lot of all for model verification, because when we try to represent urban area in numerical models, which are used for weather prediction or climate modeling, or more complex with different tuning, different nuances, and we need observational data to check what is better. And primary information for model verification is not routine temperature measurements, for example, but flux measurements. Because in the models, firstly, are calculated, firstly flux are calculated, and only then diagnostic temperature. So it's more efficient to see what's going with flux. And this is why we need flux measurements for urban areas. And this is an example of big model intercomparison project called Urban Plumber. It collects observations from towers and many sites and many models. And this is an example how model is evaluated against observations. So black line here is model. Red line is observations. Red line is model, black is observations, and it is sensible heat flux, so amount of energy which comes from surface to atmosphere via turbulent eddies. And so it's in this project is in the beginning, and very soon we will know which model is better according to all these varied measurements. This story was about the lowest part of atmosphere, just near the surface. But when we are speaking about relevant processes such as air pollution of air dispersion, wind, different wind effects, wind energy, aerodynamic of buildings and other constructions, it's very important to understand what's going above the surface in the few lowest 100 meters or even few kilometers. This part of atmosphere is called atmospheric boundary layer because it's directly affected by the surface atmosphere interaction. So in this part of atmosphere, we have diurnal cycle, we have dispersion of pollution, and etc. And all urban climate effects are mostly localized in this part of atmosphere. And the problem is that there is a strong lack of data for this part of atmosphere, both for rural and urban sites, because near the surface, we have weather stations, we have masts, we have different remote sensing equipment, such as wind sonars in this photo. And at some significant altitude, we have aircrafts, we have weather balloons, but we have almost nothing in this gap. And only very recently, we got an opportunity to make much more measurements in this area. And this opportunity is given by development of drones, quadcopters, or small planes. This is emerging method in atmospheric sciences, and there are now many different groups which developed their own models and running experiments with different drones to measure geological profiles in the lower atmosphere and the boundary layer. And there are some very advanced equipment, for example, copter zone that's specifically designed for atmospheric measurements in lower atmosphere, and this is commercial model from Switzerland. Also, very useful measurements could be done by mass market DJI drones if we just put some sensors to these drones. So we, with Pavel and colleagues from IMO Buchhoff Institute, have experience in running these drones. So this is, for example, measurements of temperature profile during a strong temperature inversion in winter. And this is wind speed profile, because drones are also possible to measure wind speed just by their inclination angle. And now this area, as I already told, is very rapidly developing. And for example, this company Meteoromatics in Switzerland, it already developed models which could automatically flight without any without need to have a pilot. So there is only an operator which is looking that everything is okay, and drone automatically starts, make measurements, lands, and recharges. So it's the nearest future for the meteorology. And this is an example of how drones could be applied for urban climate studies, because it's especially difficult to make boundary layer measurements in the cities. And drones is very good opportunity for this. And we'll tell later, we have ongoing studies about urban climate in the Arctic, because this area has a big lack of any observations, and there is a problem of atmospheric inversions and associated air quality problems. And in winter in Arctic cities, we have very strong urban heat island, because there is very cold and buildings are heated. And even the small city like Nadim, it's a city in Siberia, somewhere here, with population about 50,000 people, it could have very strong urban heat island with different temperature difference more than 5 degrees. And urban heat island develops when we have inversions. So it's very interesting to look what's happening above the city in such situation. And we use drones, this low-cost DJI Phantom drones with attached sensors to see what's going on. It was a very cold experiment because there was -40 outside. In some cases, here are examples where were a bit warmer, about -30. And we get this data that there are very strong temperature inversion outside, but in the city atmosphere remains mixed in the lower, its lower part, in lower 50 meters. And it's very important because mixing such properties directly determine the mixing conditions and air quality. So this is the first estimate of boundary layer, urban boundary layer study for an Arctic city. So yeah. And if we will dream a little bit about how drones could improve urban measurements in nearest future, we can imagine as well as dense 3D observational networks, which will provide very dense and regular observations like we have now for weather stations, but for imagined that we will have a lot of drones flying over the city, for example, for delivery, for monitoring policy operations. And all these drones will be able to send their meteorological measurements to cloud, like now we have AMDAR meteorological observations from commercial planes. And one more issue which I would like to tell about, it's so-called non-traditional data sources for urban measurements. Now we have very rapidly developing areas where we have crowdsourcing information. In other words, data generated not by professionals, but by enthusiasts and just regular citizens. And also, this is densely related with Internet of Things, when we have different gadgets, and these gadgets provide some information which is collected together somewhere in the cloud. It could be accessed and analyzed as big data. And examples relevant for urban meteorology are, for example, processing of temperature observations from smartphones or smart clocks, smart watches. There are now several studies, and they provide evidence that some information, of course not very perfect, could be taken even from such approaches, from the smartphone or smartwatch. Another example of crowdsourcing, probably less relevant for urban studies, but still very interesting, is information about rain wipers in the cars, because now cars have rain sensors which switch on and off wipers automatically, and this information could be accessed and used to estimate special distribution of the rain and to improve weather forecast. And of course, this is very relevant for urban areas because rains could be very bad for big cities, intensive rains, and we need to warn them as best as we do. Probably the most developed area in field of crowdsourcing is work with citizen weather stations. Nowadays, citizen weather stations become more and more popular as IoT gadgets. So people buy stations, install them at their homes just to have actual information about weather in their smartphones. And this is an example from Netatmo weather station, which is the world's largest network. And this is a really huge data. For example, in Paris, there are more than 6,000 such weather stations. It is several orders more than the number of weather stations from regular networks. In this example, how this data could be used in urban climate studies for Berlin, for pioneering research from Meyer et al. 2017. So you can see that here squares are regular professional weather stations by German Weather Service, and black and circles are citizen weather stations. You can see that with citizen weather stations, we have much more information. Of course, there are some problems when we work with such information because nobody controls how the station is installed and what measurements it provides. It is some examples from our study for Moscow. This is all data we collect from citizen weather stations for summer and winter. And there are typical problems. For example, in summer, we have many stations which are overheated by sun, which means that they are, example, installed on a heated wall, not in the shadow as recommended by manufacturer. And in winter, outdoor sensors inside buildings, or put, I don't know why, put their stations in the fridge. And they provide about 0 degrees during summer. But all these problems, not all, but most of them could be filtered using quite simple statistical approaches, which are already developed. And so if we filter all these artifacts, we still have about 50% of data, which is really a lot. And this is what we could get about Moscow urban heat island from this data. So here again, we have circles and squares, different types of official measurements, and small circles, citizen weather stations. So again, much more information than official data. And this data could be used not only for scientific research, but for improving weather forecasts. And here there is pioneering experience from Norway. Norwegian Weather Public Service already takes this data and assimilate it into its numerical weather prediction models. And this provides significant improvements of the weather forecast. And here are examples for Oslo. You can see how many citizen weather stations exist in Oslo. They could be quality controlled and filtered and then put into the model. And we have quite significant difference between model experiment without observations and with observations. And such citizen networks are developing not only for temperature, but also for air quality. And for air quality, people are motivated by the fact that official air quality information could be somehow misrepresentative because government could probably don't want to share real data about air quality. And people want to have their own network, and it's also very fast developing. So this is sensor community network, which include several hundreds of stations for Moscow. So here people not buy the weather stations, they make it not weather air quality unit by components from air quality patterns for Moscow. And key advantage of citizen data is that it's typically opened and could be accessed by any external software using special protocols, using special API. And together with colleagues, we are developing a service which takes data from Netatmo network, also from official observations for Moscow. And it is demonstration how data could be used to monitoring what is going in a big city. So it's an example how it looks. There are observations for Moscow for recent winter, and it's example of the strong urban heat island. So we have about minus 50 degrees, minus 15 degrees in the city center, and minus 26 outside the city. So we could just look what's going on. So it's example of our application. Do you see it?
Yes.
Yeah, of course. Okay, perfect. So this is example how different types of data looks. So we can open some example. So this is a case, or I was showing in presentation. So this is very strong winter urban heat island. And we can see temperature itself or urban anomaly of air temperature. So we can see that city is 10 degrees warmer than rural area. And of course, we could see not only temperature, but other parameters. And another interesting case is associated not with urban heat island. Here it's summer case. And here we see urban, here we see the south of the Moscow, and it is associated with
Mikhail?
measure about available urban climate measurements. And I will not repeat details, and we'll give the floor to Pavel, and then we will together answer the questions.